Hey guys, in this video I'm gonna show you the fascinating theorem, which is Ascoli-Arzela theorem. And this video we're gonna include the theorem itself and how we are gonna prove it. So in proving it, the process of proving it also includes some other like lemmas and theorems. And we're gonna still introduce a very critical concept called equicontinuity to finally reach the result of that theorem. So, if you don't understand what I'm gonna talk about in this video, it's totally fine, cause what I've already uploaded to my YouTube channel, and the content in this video, there exists some gaps. So it's totally fine if you don't understand it, but if you want to read more about it, you can actually refer to the book. I think it's Walter Rudin's Principle of Mathematical Analysis, if my memory is right. I will later put the book name and the author's name to the information bar, so you can go and check it yourself. Okay, now let's get started. So actually, before I formally introduce this theorem to you, I wanna start with the motivation to this theorem, or something like why we wanna get to the result of the theorem. So I think it's just from my perspective, I think the motivation of the Ascoli-Arzela is something from Bolzano-Weierstrass theorem. So sometimes we just abbreviate as BW theorem. So Bolzano-Weierstrass theorem said every bounded sequence of real numbers has a convergent subsequence. I will not prove the theorem in this video. We may cover this content in previous video. I might cover the content of this theorem in the following videos, but I'm not gonna prove it in this video. So actually, more generally, the Bolzano-Weierstrass theorem can be expanded like every bounded sequence in Rn has a convergent subsequence. So Bolzano-Weierstrass theorem kind of focus on the sequence of numbers, sequence of values, but what if we expand it a little bit to be like a sequence of functions? So under which condition, if we are given a sequence of a sequence of functions on certain set or certain matrix space, under which condition can we find a uniformly convergent subsequence? Or can we find a uniformly convergent subsequence, or there exist? So this is basically the content or the aim to Ascoli-Arzela theorem. So let's first introduce you some theorems other than Ascoli-Arzela to help us reach the final result of that theorem. Okay, the first is, now we are now given a sequence of functions, a sequence of complex valued functions on E, Fn. And the conditions are, the first one, now E is countable. And the second one is Fn is pointwise bounded. Just in case you guys don't understand what is pointwise bounded, so pointwise bounded is just if you fix any. Well, now we're given a sequence of functions. So if you fix a point x0 in that sequence of functions, then you will get a sequence of actually real, not necessarily real numbers, but you will get a sequence of numbers, sequence of values, right? And that sequence of values is bounded. And for every x you take, you can always find some bound for that sequence of values. So this is what is a pointwise bounded sequence of functions. So under these two conditions, we can have that there exists pointwise convergent subsequence f and k on E. So we are getting closer and closer. Now we can find a pointwise convergent subsequence on E. Okay, so how are we gonna prove that? In this proof, it's like we are gonna try to construct such kind of candidate subsequence that satisfy all these conditions, and it is a pointwise convergent subsequence f and k. So starting like this, well, the condition says that it is countable. What can we do with a countable like set? So since it is countable, we can actually let it be the form like E equals xi. I is from I to infinity, right? I is from 1 to infinity, because it's countable, right? And also we know that Fn is pointwise bounded. What does that mean? If we take x1 from the set of to the set of the set of points E, like if we fix x1, then we get Fn x1, and from 1 to infinity is bounded, right? Because Fn is pointwise bounded. Now we fix the point x1. Okay, just as I previously mentioned, now if we fix a point xi, now the sequence of functions become a sequence of numbers. So by Bolzano-Weierstrass theorem, we have a convergent. There exists a convergent subsequence f and k, where k is from 1 to 0 on x1, convergent on x1, right? We'll give it a notation like, okay, we'll notate f1k to be fnk. So 1 here is just, 1k here means the case element of sequence that of the sequence that convergent to x1. So one here stands for x1, and k means we take the case element of the sequence that we take from that converge to x1, converge uniformly. Okay. Oh, I'm sorry, it's not convergent uniformly, because it's just a sequence of numbers. So the sequence convergent to x1. Okay. Now we continue to do so. Now we know that so we've already take the subsequence of the original sequence f and x1, and we still take the subsequence of the sequence that we just take. Now we have f1 and x2 if we fix the point x2, where n is from 1 to infinity. This sequence is also bounded, right? Because Fn is a pointwise bounded sequence, right? So still, by Bolzano-Weierstrass theorem, we have a convergent subsequence f1 and k. So sequence convergent on x2, right? And still we notate it as f1 and k. And 2 here stands for the x2, so the sequence is convergent on x2, and k still means the case element of the sequence that converges to x2. And since it's the subsequence of the sequence we take from x1, from the sequence that converges on x1, so you know that actually the sequence here we take converges not only on x2 but also x1, right? And if we continue to do so, we will obtain so continue to do so. We'll get something like this. F11, F12, F13, blah blah blah. The sequence is convergent on x1, right? And F21, F22, F23, convergent on x2, F31, F32, F33, convergent on x3, and further. Okay, now we obtained some all these sequences, all these functions. So what now? What are we gonna find out in this set of functions? We actually can observe. Okay, now let's make some observation. So I'll move this part to the next page. So we can easily get access to it. So we make some observation. First, we say that each row is the subsequence of the earlier row, right? This is actually how we obtain the following sequence. So we take the subsequence of the first sequence, right? We take the subsequence from the previous sequence that converge on the previous point, right? So this is very straightforward. This is how we get all the sequence. The second one is the nth row convergent. The nth row is convergent on xn and or xk where k is smaller n. And this is also the result that I've already talked about, right? The second row is convergent on x2, and this is a subsequence from a sequence convergent on x1. It's also convergent on x1, right? And the following sequence are the same, have the same properties. Okay, the third observation is that, and this is, I think it's the most critical one. The case element in nth row occurs in position I, where I is larger than or equal to k in previous row. So for example, like if we want to show f22, this element is actually occur in the first row, the first sequence, the first row of sequence, and it must be. It can't be the previous one. It can't be f11. It can only be from f12 to further after f11, right? Because we take all the sequence from the subsequence of the previous ones, and the sequence we list here are orderly listed, or are all orderly listed. So if you take, if you take like f33, it can only be after f23. So if you try to like if we try to like prove it in contradiction, so say if now f33 is equal to f22, it's not gonna happen, right? Because if f33 is equal to f22, then how do you get f31 and f32? The second row is a subsequence of the previous row, previous row. So if f33 equals to f22, then you have only one element, f21, and f21 cannot be equal to f31 and f32 simultaneously, right? So it's not gonna happen. Okay. Well, based on this observation, we can now finally get the subsequence we want. So if we like take all the diagonal elements, then the sequence of functions f and n actually converges on each row, on each of the xk, right? Because if you take the diagonal element f1, f22, f33, you kind of like guarantee that every element you take is convergent on the row that exists and the row before, right? Because it's actually the it's actually the because the way we take this following sequence is always the subsequence of the previous sequence, and also since the element you take can only occur after the sequence, after the element of the same position in the previous row. So if we take it diagonally, you will not get like repeated functions. So that's how we get the like satisfactory sequence f and n that converge on each of the xk. And in fact, it's very straightforward to prove that f and n is pointwise convergent subsequence. And I'm not gonna write a formula on how to prove it, because we already illustrated on like how to construct this this sequence of functions. Okay, so here is a question you can think about a little bit. It's very simple, but you might want to think about it. So if we are given a function, a sequence of function which is uniformly bounded, and it is pointwise convergent on a compact set. Sorry. Can we get that there must exist a uniformly convergent subsequence? So we'll like have a go at how to like set some conditions to finally find the uniformly convergent subsequence. So we let Fn to be uniformly bounded. Condition 1, uniformly bounded, and 2, pointwise convergent. And condition 3, the set is compact. Can we get a uniformly convergent subsequence under these three conditions? Actually, no, it's false. And we have actually an example, or you can take it as an exercise. You can check fnx equals x to the n on the compact set 0, 1, and you will see that there is not such kind of uniformly convergent subsequence. Okay. So now, since the conditions we just the conditions that we just wanna use to get the uniformly convergent subsequence that doesn't seem work well, then we somehow need to introduce some more strict or more sophisticated concepts to help us find the conditions for uniformly convergent subsequence. So now we're gonna move on to equicontinuity. So let me give you the definition of equicontinuity. So here, f is a family of functions from E to the complex numbers. A family of functions is same as a collection of functions. And if now for each epsilon larger than 0, there exists a delta larger than 0 such that for any 2 points xy, their distance is smaller than delta, you can imply that fx, xy, the distance fx minus xy, this distance between fx and xy is smaller than epsilon, and here the f is arbitrarily chosen, so it is satisfactory for all f that is in the collection of functions. Then we say such kind of family of functions, collection of functions, is an equicontinuous function. Equicontinuous family on E. So we've already have continuity and uniform continuity, and now we're introducing equicontinuous. What's the difference between them? So it's very obvious that the condition is getting less and less stricter, right? Because in the past, if you wanna prove some functions continuous, the delta you choose should be dependent on three elements, three aspects. So it should be dependent on the epsilon that you choose, and x, so it's dependent on which point you choose to prove it's continuous, and the function itself. And for uniform continuous, it's less stricter because you only consider epsilon and the functions, right? You don't consider x because it satisfies for all x. And then now we are moving on to equicontinuity. So now the delta you choose only dependent on epsilon, because it satisfies for all functions in the family of functions f. Okay. Actually, we will make some remark here. Well, let's say if you are given here f is a family of functions, right? So a family of functions or a collection of functions can be infinite, many, or finite. So if the collection or if the family is finite, so you're given a finite collection or family of uniformly pay attention. Here, a finite collection of uniformly continuous functions. Is this family of functions equicontinuous? Can we get that? Actually, it's true. Why is that? Well, simply because it's finite. Since it's finite and all the functions here is uniformly continuous, then you can always find the like the smallest one. Smallest, just find the smallest delta, and that delta works for all functions. Okay, this is very simple and straightforward, but we're gonna use this remark in the following theorems. Okay, the next theorem is well, it's closely relevant to equicontinuity. So now we are given still a sequence of functions, and this sequence of functions are actually continuous on a metric space K. So the condition now is, firstly, K is compact. Okay, K is compact. And the second is Fn, the sequence of functions converges uniformly on K. And now we can get Fn is equicontinuous on K. Okay, so it's like from continuous function to try to the sequence of functions are continuous and the set is compact, and sequence functions also converges uniformly, and we want to get equicontinuity. So, the proof of this theorem is I think it's actually very like straightforward, or it's just based on the definition of equicontinuity, and also you are gonna use the very classic method in like proving it, because I call it a classic method. It's actually triangular inequality because I use a lot of times to prove the theorems or lemmas in theorems or lemmas concerning like uniform convergence or pointwise convergence. It's something like you see that you want to prove something is convergent uniformly. The minute you say it, something like triangular inequality just pop out in your mind. So, in other words, we want to show, well, by definition, we want to show given epsilon larger than 0, there exists a delta larger than 0 such that if we find any point xy and its distance is smaller than delta, we can imply that fnx minus fny is less than epsilon. Okay, now let's try to prove it. Now let's first fix a epsilon. Well, it's because we are given epsilon and we want to find some data, so let's first fix epsilon. And so we look into the conditions we have. We have uniformly convergent, right? So by uniform convergence, there exists an n such that when n larger than n that we choose, we actually have fn x minus fn x is the absolute value of the difference of these two terms is less than epsilon over 3. And this is basically from Cauchy criteria of uniform convergence. Right? Since fn converges uniformly, yeah, you can get that point. For any epsilon, you can find some n such that when n larger than the capital N, fn x minus f capital N x is the absolute value of the difference is smaller than epsilon over 3. Okay. And where this n, since we can find such kind of n, and we know that n and now is a number, it's finite, right? So if we take the set of these functions f1 to fn, this is a finite collection of functions, of actually finite collection of uniform convergent functions on a compact set. Okay, so now by previous remark, finite collection of uniformly convergent, uniformly continuous functions. Well, I think I don't need to mention more because it's the set of functions are continuous, and it also converges uniformly. So it's easier to say that it's the set of functions actually continues uniformly, right? So uniformly convergent sequence, or it's uniformly continuous. Then by the previous remark, we get that this set of functions is actually equicontinuous. Great. So, since it's equicontinuous, we can use the definition. There exists delta larger than 0 such that when xy, the distance between xy minus is smaller than delta. It implies that fix, I is from 1 to n, fix minus fiy, distance between these two terms, is smaller than epsilon over 3, right? And this delta satisfies I think this delta actually works for f1 to fn, right? But we want to show that this delta actually works not only for f1 to fn. We want to show that this delta also